So we have seen in other videos that charged particles moving through a magnetic field experience magnetic forces. Well, what you see in front of you is a current carrying wire, and I've made the wire kind of a, not a nice, pretty straight shape. We like dealing with straight wires, and we will deal with straight wires, but to start this discussion, let's just imagine that this wire can take any shape it can, which, of course, in real life it can. You can bend a wire into whatever shape you want to. And we'll say that this wire is carrying a steady current, steady meaning not changing in time as far as the strength of the current. And this is going to be passing through some magnetic field. I've also drawn in here some differential charge. Of course, a current is a moving charge, so this dq is going to move. It was up here, came down here to where I've drawn it, took a snapshot here. It's going to continue on down the wire, but this is some differential charge element that is making up part of this current. I've also drawn this dl vector. What the heck is this? Well, dl is always just a placeholder for some sort of spatial differential, some sort of directional differential like a dx or a dy. To make it general, I'm going to write dl. If I come up with against a wire that's horizontal, I'm probably going to change dl to dx. If I come up against a wire that's vertical, I'm probably going to change it to dy. If I come up against a wire that's in a circle, I'm probably going to change this to some rd theta. We've seen all of this before. But the idea here is this is a differential element of the path. What path? The path of the wire. So if I was going to integrate dl, what I would get is I would integrate it along the path of the wire. Fair enough. What am I going to do with this? Well, we know that charged particles in magnetic fields experience magnetic forces. And a current is nothing but a collection of moving charges. That's how we define the current, dq dt. So here's a differential charge element of this current. This is going to feel a magnetic force. I can write down that force. I'm going to write it as a differential of the force because I understand that there's a dq here, here, everywhere. Each one of those dq's is going to feel some small bit of force. If I then integrate, I add up all of those little elements to come up with the total force. But right now what I'm going to write down in order to have something to integrate is the differential contribution to that force by the differential charge element dq. All right, I get the charge dq times its velocity, and I should make this a vector, times its velocity cross B. I can put this in parentheses if you want to. This is the full calculus treatment of the magnetic force due to a charged particle moving with a velocity v in a magnetic field B. Of course, if I want to determine the entire force on this wire, I'm going to integrate this expression, but the problem is integrating this is not going to be trivial. Notice that V is not constant, not that that's a deal breaker, but I can do a little work here to put this in a form that I think is going to be easier for me to evaluate. So I'm going to have to play a little fast and loose with the calculus. Sorry, calculus teachers. Let me rewrite dq, not dq, let me write v as the definition of velocity, which is dl dt. And I hope this doesn't confuse you. In physics 1, you probably saw this as a dx dt, dy dt. dl just tells you that the velocity has to take into account the actual path, the actual displacement. So this is my differential displacement element. The time derivative of that is going to get me the velocity, and then cross B. All right, so here's where I'm going to play a little fast and loose with the calculus. I'm not really. We get away with this pretty easily, it's kind of hand wavy, but we justify this pretty easily by noting that in the physical universe, we don't ever actually deal with an infinitesimal differential. We deal with a really tiny delta that we treat as this, but okay, fair enough. If I make that general assumption and maybe hope that no calculus teachers watch this video, let me rewrite this as that, where I'm now taking the time derivative of the charge. Well, what is that? dq dt is just I. So I come up now against this expression, which turns out to be a heck of a lot easier to evaluate, I think, than this expression or this expression. And it's because I've assumed that I is steady. That is to say, dq dt is actually not, there's no time rate of change of the current. Of course, definitely is a time rate of change of the charge. It's moving. But there's no time rate of change of the current. So this is steady. Now my integration just has to be an integral along some path. We're going to see how to evaluate this in a simple example. But just to reiterate what I've done, what I've come up with is the differential force contribution of this differential charge element moving in this magnetic field by using the differential displacement element that lies along the path over which the charge is moving. Okay, let's do a simple example. Simple means I'm going to use a straight wire and a steady current. So let's put a magnetic field in this region, which looks like this. Fair enough. So here is my current. Here's my current carrying wire. We're going to let this have a length L, and I'm going to determine the magnetic force acting on this wire due to the magnetic field. Fair enough. I get dF is equal to integral, I'm going to write it like this, I times integral dl cross b. This should be a vector. I pulled the I out of the integral because I said, well, I'm going to assume a steady current, which means I is a constant. This is going to be an integral over some limits. Let's just set my coordinate system 0 here. I'm going to put my origin here, which makes this point L. This is the coordinate L now. So I'm going to integrate from 0 to L of dl cross b. Now, I'm going to submit that in this case, we don't really need to go through the calculus because it's going to be easy to see what happens. But let's go through it a little bit so you can see the process. I need to write these in a form which makes sense to me to be able to integrate. So what I'm going to get here, I integral 0 to L. Instead of writing dl, which remember is my placeholder, here I'm moving to the right horizontally. If I'm moving horizontally, I might as well replace this placeholder with a dx, something I know and love. And of course, it's moving in that direction. This is a vector, so I need to make this a vector. Easiest way to do that I know of is to put on the vector dependence with a unit vector in the x direction. Cross b vector. Now, notice this is into the page. Let's just say that this is b b negative k hat. Into the page. All right. You can define that as positive if you want to. You find lots of people that do. It doesn't really matter to me. I'm just showing you the way which we turn this integral into something that makes some sense. What that allows me to do is take care of this cross product in the integrand. Notice what I'm going to get there is I integral 0 to L of b dx. I just rewrote them, but I flipped the order of the coefficients because they're coefficients, they're scalars, they commute. And then I have I cross minus k hat. Now, I can go through and determine what this actual vector is, and in some situations you'll need to. I'm going to stop this here because what I'm going to do, which is what I typically do and encourage you to do, is not care about this yet. Why am I doing this? To determine the direction of the force. Well, can't I determine the direction of the force with simpler means? That is to say, the right-hand rule. Yes, I can. And so what I'm going to do, what I would have done from the beginning here, is thrown away the directional information, make this a magnitude equation, and find the direction based on the right-hand rule. I'm showing you this here because pretty soon we're going to run up against the Biot-Savart law, and I'm going to need to be able to do this for the Biot-Savart law. In this case, though, I think going here is the long way around. And so I hope it's okay that I've shown you this. I want you to see the process and understand how I turned this into this and ultimately into this. Notice when I evaluate this, it's going to be a constant unit vector I can then pull out of the integral and just evaluate this. But let's just forget about that for a second. Let me take an absolute value here. I integral 0 to L of b dx. What have I done? I've taken the absolute value over here. This is going to be a unit vector by absolute value that's 1. And so what I'm doing is I'm throwing away the directional information here. And I'm going to add it back in later by inspection. All right. Hopefully that's clear. Well, b is also, as I've drawn it, steady. I shouldn't say steady. I should say a constant in magnitude and direction. And what I'm going to get here is then b integral from 0 to L of dx. This is about the easiest integral you're ever going to evaluate. What I'm going to get out of that is I'm going to write it in the standard way people do, IL b, where L comes from the evaluation of this integral. Turns out this is the magnetic force on a long straight wire. I need to do that. If I'm going to integrate both sides, I need to do that. My apologies. If I'm integrating this side, I got to integrate this side, right? So what do I get when I integrate this side? I get the force. And the force is then equal to ILB, which is the magnetic force that acts on a straight wire of length L, which is carrying a steady current I in a uniform magnetic field B, just the length of the wire. You could look at this equation and figure out that you could get there pretty easily just from recognizing that if DL is a path over this length, well, that's a straight path of length L. This is going to have to evaluate to some sort of capital L. So the calculus, I think, in this case is a little bit more complex than just reasoning our way through, but it's important to be able to do this. It's important to be able to turn this expression into this and this. Now, if I had evaluated this would have gotten me my direction. What I'm going to do is get the direction from the magnitude, or I'm going to get the direction using the right-hand rule and attach it to the magnitude. So, right-hand rule. Well, remember, if these are charges that are moving, the velocity is going to be in the direction of the current, right here, this current. So I'm going to put my fingers, just my right-hand rule, in the direction of the velocity. I'm going to curl them into the direction of the field. Right, so fingers in the direction of velocity, curl them into the field, stick out my thumb. Now, when I was doing charged particles, what I did now was to check the sign of the charge, but I'm always going to consider a current to be a movement of positive charges. Do I have to do that? No, but I am always going to consider a current to be a movement of positive charges unless I'm dealing with something like a plasma and I have charges moving in both directions. We're not going to do that in this course. All the currents we're going to deal with are positive charges moving, so I don't have to worry about that rule that said check the sign of your charge. I put my fingers in the direction of the current, curl them in the direction of the field, stick out my thumb. That gives me the direction of the force. This wire will feel a force upwards like that. So this is the direction of the force. That enables me to do something simple like this. Force is equal to ILB. Let's just say J hat. And the upwards Y direction, if you want to call that J hat. Okay, hopefully that makes some sense. Hopefully I didn't lose anybody here, especially by doing it and then throwing it away. But I really think this is important to be able to do. Probably not in this case. This is a little bit more trivial than this. But if you're doing a wire, which is crazy, you're going to have to do something a little bit more intense here. And again, when we come up to the Biot-Savart law, we're going to have to talk about how to deal with this. So try to understand what we did moving from here to here, turning this DL into this DX I had, and so on and so forth. All right, so that is the force on a current-carrying conductor, a current-carrying wire. There's something else to talk about in this section, though, which is that we stated before that all magnetic phenomena arise from moving charges. Well, what is a current but a moving charge? So interestingly enough, if I have a current, that current produces in and of itself a magnetic field. This was first noticed in the laboratory when it was noticed that turning a current on and off caused nearby compasses to deflect momentarily. So the magnetic connection between currents and magnetic fields was established experimentally, quite by accident actually, wasn't noticed, but it turns out that this is the case. I'm going to draw in the field of this wire. We'll talk about how to get it. Of course, I'm drawing at one point the field of this wire. I could draw it bigger if I wanted to. It's going to get convoluted really quickly. But the idea is the field of this wire is going to propagate out in space. It's going to get weaker as I get farther away from the source, which is this current. That is probably not surprising. Every force we've seen gets weaker as you move farther away from the source. Magnetic forces are going to be no different. Magnetic forces arise from currents. So the farther away you get from the current, the weaker the force is going to be. We're going to see in the next section the expression for that force. Right now we're just talking about the direction though. So how did I get this? Well, first of all, I would say this is a little bit hard to read, and that comes because I am I'm on a two-dimensional surface, and I'm dealing with this three-dimensional system. So let me draw this a little bit more rigorously. Here's my current. And here is my magnetic field. So what is happening is it's coming out of the page here and back into the page here. This is why I do these loops. It's forming loops, so it's coming up behind the wire, out of the page, in front of the wire, back behind the wire. It's coming out of the page, looping over, going into the page, looping under, coming back out. If I were to draw this wire looking down it from this direction, so if I were to put my eye here, it's a terrible eye, but that's the idea. If I were to put my eye here and look down the wire is coming at me like this, and the magnetic field is forming circles around the wire that look like this. So here is where it's coming out of the page, here is where it's going into the page. It forms concentric circles around the wire. How do I determine the direction? Well, it turns out there's another right-hand rule for this. So it's not the same right-hand rule that we've been using. It's actually a little bit simpler. We're going to see this rule several times, and so I'm going to give you my most general expression of this rule. Number one, you want to put your thumb in the direction of what is straight. Okay, what is straight here? I think maybe it's obvious that the wire is straight. The magnetic fields are curved, but the wire is straight. So I'm going to put my thumb in the direction of what is straight. Then the curl of my fingers shows direction of what is curved. My thumb is going to be straight, my fingers are going to curl. In this case, the wire is straight, so I'm going to put my thumb in the direction of the current this way. And then my fingers are going to show me the direction of whatever's curved. In this case, that's the magnetic field. And notice I have it coming out of the page up here. If my thumb is in the direction of the current, my fingers above the wire are coming out of the page. Of course, they're going to curl on around. I have to put my hand in strange position. And down here, they're going to go into the page. So let me flip my hand and look down the wire like I did here. So here's my system. Look down the wire. You get above the wire. The magnetic field's coming out of the page. If I curl on around, if I curl on around below the wire, the magnetic field will be going back into the page down here. So the thumb in the direction of what is straight, then the curl of your fingers shows the direction of what is curved. In this case, the current is straight, which means the field is then curved. As you can imagine from how I've said this, we're going to see the opposite situation at some point. But for now, I'll try to hang on to this right-hand rule and try to understand how we get the current direction from this. One more thing to talk about if we understand that. Let me take two current-carrying wires and put them near each other. So I'll do this one in black. I'll do this one in red. I'll put them going in the same direction. Why not? Make sure I can see that. Good. What I'm going to draw, now both of these wires, I should say this will be I1. Oh, can't see that. I1. Move over, come on. And I2. Now, both of these wires are going to be both of these wires are going to be producing a magnetic field. If I draw the field from both of these wires, it's going to get really convoluted. So I'm just going to draw it from one. I'm going to draw the field from this bottom one, I2. Let me put my fingers in the direction of the current. Then my fingers, no, sorry, I'll put my thumb in the direction of the current because the current is straight. Thumb in the direction of the current, my fingers will then give me the direction of the field. So it looks like everywhere up here, the field from I2 is coming out of the page. That's here, here. Now again, this magnetic field is not going to be uniform because it will weaken as I get farther away from the source. But everywhere up here, I get a magnetic field that looks like that, and everywhere down here, I get a magnetic field into the page. I'm only going to draw one line because I really only care about what's going on up here. Because what I want to know is what happens to I1 because of I2, right? If I2 is producing a magnetic field, that magnetic field will exert a force on I1. So I got this field from using this right-hand rule, thumb in the direction of what's straight, fingers in the direction of what's curved. Now I need to determine the force. So I need to use the right-hand rule for forces. What I just showed you, I will call the right-hand rule for fields. Thumb in the direction of what's straight, fingers tell you what's curved. Right-hand rule for forces says put your fingers in the direction of the current or the velocity, curl them into the direction of the field. Your thumb will tell you the direction of the force. So if I put my fingers now in the direction of the current I1 and curl them into the field, well, the field's coming out of the page, and so I'm going to have to flip over my hand and curl them out of the page, then stick out my thumb. I get that there's a force exerted on I1, which is downwards. So what's happening? I2 is producing a magnetic field, which is then exerting a force on I1, which is attractive. Attractive to what? Well, notice I1 is being pulled towards I2, so that force is attractive. I2 is producing this field. This field is interacting with I1, producing this attractive force. Okay, if we can hang on to that, let's flip it around. Okay, fair enough. What force is I2 feeling due to the magnetic field of I1? Now, how could I do that problem? I could redraw this and draw in the magnetic field now from I1 and not I2. And then do the same process on I2, fingers in the direction of the current, blah, blah, blah. But you might be able to guess what I'm going to get. I'm going to get a force on I2, a bit of a different color, that looks like this. How do I know? Well, mainly I know because Newton's third law is still a thing. And if I2 is producing a force on I1 that looks like this, I1 must be producing a force on I2 that looks like this. Equal and opposite, same in magnitude, opposite in direction. Newton's third law makes this really, really easy. Of course, I said a while ago that this is an attractive force because it's pulling I1 towards I2. If it's an attractive force there, it's got to be an attractive force here. It's got to pull this up. So however you want to get there, redraw the system, put in the magnetic field, do the calculations. That's fine. I think it's much easier to just use Newton's third law. You've already done the hard work. Rest on your laurels for a little bit. Let Newton do a little bit of the work. This has got to be the force exerted on I2 due to I1. We will see the form of this force as far as between the two wires in the next video.